I want to discuss a few simple resistor networks and how to calculate them. So the equation for the series resistance was that R1, so plus R2, is R, right? If we have two resistors in series, like R1 and R2. But what happens if we have another resistor here? So it can be shown that that would also work for more resistors, right? So R1 plus R2 plus R3 is the effective resistance of three series resistance R1, R2, R3. So in general, we can say if we have series, so resistors in series basically, we would say that the effective resistance, the total resistance of this network is the sum of all the resistances, index k from 1 to n, if you have n different resistors. In parallel, let's say we have parallel resistors, R1, R2, R3. R1, R2, R3. Then parallel resistors. So we can generally say that, so this is for series, and the effective resistance of the parallel resistors is 1 divided by Rp, so to the power of negative 1 is then the sum of the reciprocal resistances. Okay, for example, 1 divided by Rp is 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. So in this case, this would be the sum of the index k runs from 1 to 3, so it starts at 1, it goes to 3, and we are summing up 1 divided by Rk, right? Okay, so parallel resistances and series resistances. So, but what do you do if you have mixed combinations? We discuss only a few simple cases. More complex cases would have to be solved with Kirchhoff's law, which will be introduced later. Let's make an example. How does it look like, the example? I don't know yet. Let's say this is R1. And then we have two other resistors, and these resistors are now in parallel. R2 and R3. So in this case, it would be easiest to calculate first the parallel resistance of these two. And let's call this, I don't know, Rp. So you could calculate Rp by saying Rp is, so 1 divided by Rp is then 1 divided by R2 plus 1 divided by R3 is 1 divided by Rp. And if you are, so then you would need Rp itself, which means it follows that Rp is then 1 divided by R2 plus 1 divided by R3 to the power of negative 1. So 1 divided by this, right? This would be 1 divided by R2 plus 1 divided by R3. So that can be simplified. So we multiply with 1. So we are multiplying by 1. And 1, we express 1 as R2 times R3 divided by R2 times R3. So when you see, this fraction is of course 1. So we are multiplying the numerator to the numerator and the denominator to the denominator. So 1 divided by 1 divided by R2 plus 1 divided by R3 times R2, R3, R2, R3 is equal to R2, R3. And here we have to be careful, right? Because we multiply now the denominator here to the sum of this denominator, which means we have to apply the law of distribution, which is then 1 divided by R2 times R2, R3 plus 1 divided by R3, R2, R3. And you can see now, this and this cancels, and this cancels. So that was a mistake, so that what remains is R2, R3 divided by R2 plus R3, right? So that would be directly your R parallel. But you can really do the calculation first with the reciprocal resistance, right? It's sometimes easier to simply start with the reciprocal values, and you can even use fractions, and then you get nice rational numbers. We will do a numeric example soon. So because when you did this, when you achieved this, what then is the effect? It follows that your new equivalence circuit looks like this. You would have the resistor R1, and then you would replace this parallel resistor just by R parallel, like this, right? Okay. That means now the total resistance R for the whole system would be R is now R1 in series with this effective resistance made of two parallel resistors, right? Would be then R1 plus R2, R3 divided by R2 plus R3, right? This is an example how you do it. So if you have a different configuration, let's say this would be example 1. Let's have another example. Let's make another example, and in this case we have this configuration of resistors. R1, R2, R3. So you see you have a series resistance of R2 and made of R2 and R3 parallel to R1. Okay, so that means in this case it's easier to combine these two first and say this is my RS, which is my series resistance. And in the end, I have now the series resistance RS parallel to R1, which means R divided by my total R, the effective R of the whole network, is then 1 divided by R1 plus 1 divided by RS. So we can write this down immediately because RS is nothing but R2 plus R3. That would be 1 divided by RS, R1, plus 1 divided by R2 plus R3. So with your calculator or pocket calculator, you could solve this equation first and then take the reciprocal in the end to get R, right? It follows that R is something. Or you can use the equation for the parallel resistance of two parallel resistors, similar to this one here. So, okay, if you have two resistors RA and RB, let's say this is RA and this is RB, and you're combining them in parallel, then the total resistance, the effective resistance of this simple network would be R is RA times RB divided by RA plus RB. So in case you maybe confuse or you forget where to put the plus and where to put the multiplication, you can have a look at the units, right? Because the units of R is of course ohm. The unit of the sum, RB and RA, is also ohm. But the unit of the products, the unit of RA times RB, is of course ohms to the power of 2. So this is ohms to the power of 2 divided by ohms gives you ohms. That's okay. If you do it the other way around, if you take the reciprocal, right, you would divide ohms by ohms to the power of 2. So that the units help you a little bit to memorize this formula. This important formula here for the parallel resistors. Okay, so now let's substitute the values here. Let's say RA is R1 and RB is RS, right? So then we simply substitute, fill in the values. So this would be R1 times, so RS divided, R1 plus RS, right? And now it would be, let's now fill in the values for R2 and R3, divided by R1 plus R2 plus R3. Okay, so that would be the equivalent, the resistance of this circuit. So with these simple examples, you can calculate more complex examples, and I provided some. So that is this example here. You see here 3 different resistor networks with 3 different voltage sources. And so here in this example I used then the notation, so R1, R2, R3, 4, 5, 6, 7, 8 and 9. And you should calculate this. And I share the link in the video description. And if you are smart, you can do a simulation in LT-SPICE. The LT-SPICE is a product from Linear Technology, a SPICE modeling software, which is a circuit simulation software. LT-SPICE, sorry, it's not from LT, it's from Analog Devices, not from Linear Technology. So from Analog Devices, but I think it used to be Linear Technology, and I assume that Analog Devices has probably taken over Linear Technology. So a SPICE simulator SPICE is a family of different simulation programs. So let's have a look at SPICE. That is an EDA software. SPICE. It's simulation program with integrated circuit emphasis. That's a very old-fashioned name, and the origins of this software is also very early. So the initial release of SPICE 1 was already in 1973. So you didn't have even any personal computers in those days, and it was written in Fortran. And the calculation core of this is still the same. It's still based on the very old Fortran code as well. And so, and LT Spice is one of these many spices you have. So the spice is the simulation program with integrated circuit emphasis. So it's a family of simulation programs. It's not just one product. The core is the same of all these programs, but they're using basically different features, and they are published by different companies. Good, so this is LT Spice. I will produce another video on how to use LT Spice to do this, but first of all, work on these exercises here.